Hey kids, welcome to chapter 15, multiple integrals. I don't know why with derivatives they call it partial derivatives, and with integrals they call it multiple integrals, when really it's the kind of the same phenomenon, right? Where you were taking a function in two variables or more variables and differentiating with respect to x, with respect to y, with respect to z, blah, 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 blah. You're going to be doing the same thing with integrals, right? You're just going to be doing multiple integrals in parts, really. So chapter 15, 15.1 and 15.2 is where these homework assignments are, because they kind of combined the main ideas of 15.1 and 15.2 into one video. So remember from Calc 1, the idea of a Riemann sum, right? And finding the area under a curve. And we started with a function that was always above, right? We had f of x was always greater than or equal to 0, right? So we started with a curve that always was above the x-axis, and we talked about drawing rectangles, and we could estimate the area under the curve by finding the area of these rectangles by using the left endpoint or the right endpoint or the midpoint. And in truth, it doesn't matter when you take the limit, right? Riemann, taking the limit of a Riemann sum, the limit as the number of your rectangles goes to infinity of your Riemann notation, right? And you could kind of pick any sub x here, right? That's what that's k sub star. That star just means that if you make your rectangle small enough, it doesn't really matter if it's a left, right, midpoint, or actually any x within the subinterval. Right? So that's what we did. And then, of course, we used Leibniz notation to say, well, this was, right, a little awkward and clunky, so we used Leibniz to kind of smooth out the idea of the infinite sum. We said we were starting at A and finishing at B. We did need to have continuity. We didn't have to have differentiability, but we did have to have continuity. And that, remember, each one of these things correlated to, right, the height, the function height of your rectangle times your infinitely small widths of the rectangles. You summed them up and you got area. And then, of course, we expanded that and we dealt with, well, what happens if our function actually goes below the x-axis? Then we're not talking about area anymore, but we could just negate what was below the x-axis if we truly wanted area, or if we just wanted the value of the integral. It could be a negative value, it could be 0 if the areas balance themselves out, such things like that. Also recall, another thing we did was say, you know what? We don't need freaking calculus if our function was just, for instance, a constant, right? Sure, I could, right? Let's pretend this, what is it, a height of what, 5 maybe? Sure, I could integrate from 2 to 7 of the function y equals 5, but I didn't really need to do that, right? If I recognize what this is, hello, that is just a rectangle. The area is 5 times 5, which is 25 square units, right? I could also do that for a semicircle, right? Oh, that's terrible. Right? You recognize that as, minus, as a semicircle. If I square both sides, right, I get the circle, and this is the top half. Sure, I could integrate the square root of 1 minus x squared dx from -1 to 1, but hopefully you recognize that as a semicircle and say, oh, that's just 1/2 pi r squared, where my radius is 1. right? So just a little recap of some big ideas from Calc 1. So now let's extend, just like we do everything else, right? Let's just extend this idea into Calc 3, or multivariable. So I am still going to use infinite Riemann sums, but I'm going to find the definite integral on a region of the xy plane. R stands for region in the xy plane, defined by these boundaries. This is like x1, x2. This is y1, y2. And it kind of looks like this. So you're going to have a surface. Here's my surface. And my surface is a function in two variables. My domain is a rectangular region, right? Should have said that, rectangular region. And that's important because today we are just dealing with rectangular regions, which should just be foreshadowing to what happens when my region isn't a rectangle. But for now, my region is a rectangle. So what happens if, right, I have, here's my domain, and of course all my domain, the function takes all of these points and moves them up to our surface in z space, right? Well, we are going to take any one of these points and kind of draw a rectangle, or if you want a parallelogram around it, and then we are going to take that image up to here, create a parallelepiped or a rectangular prism. That's a terrible, terrible drawing. Here's a much better one. Here's a bunch of your rectangular prisms or your parallelepipeds, and we're going to add them all up. So with the same idea that we are going to take a limit as n goes to infinity of, right, the functions, the function height, this is the height, times what? The change in the area, right? This is height, this is my z, and this is the change in the area. And of course, as you make your rectangular regions much, much, much smaller, each little rectangle smaller and smaller, this delta A becomes smaller and smaller and smaller, and we're taking a limit. And just like before, we are going to take this clunky Riemann notation and turn it into Leibniz notation, but not, we are dealing with a domain that it is in the xy plane, so we need two integrals to indicate our domain has two variables. And of course, just like Calc 1, we change the delta to a small d. Okay, and we don't have any bounds here. This region here takes care of the values. Here, you don't have to put any values. As long as if your surface is above the x-axis, I'm sorry, above the xy plane, then that expression is volume, right? Evaluating this double integral gives you volume of this space between your surface and your domain region. Cool, huh? Here is, I'm not going to go to it because it usually messes up my computer or slows it down or something, but there is a nice GeoGebra applet that there's a link to for you to kind of look at this, and you can change the bounds of the region, right? You can change where your region is, and you can make your width of your rectangles in the x direction and or length and in the y direction bigger and smaller, and you can kind of see what happens. It's a nice little visual. All right. So a surface defined by z in two variables that lies above or on the domain region calculating the double integral over that region and between the height of this function is the double integral expression. But just like Calc 1, sometimes I don't want to use and don't need to use fancy calculus, right? So look at this. Evaluate the double integral. No. Now I've given you a clue because I've said identifying it as the volume of a, I should say, known solid here. Again, so that's another clue. So here, look at my region. Sometimes my region is written like this. Sometimes it's written like this. That being like a big not italic X to say by. So -2, 2 by 1, 6. So they're saying a double integral, which means you're finding volume of a region, rectangular region in the XY plane where the height is constant. And remember, we are making the areas of those rectangles in the XY plane very, very, very small. So hello, what does that look like? Yeah, just a box. It's a 4 by 5 box, right? So -2 to 2, right, is a distance of 4. 1 to 6 is a distance of 5. And then my height is constantly 2. So thanks, double integral, fancy schmancy stuff. But I think the volume of this known solid is just area of the base times the height. The height is 2 times the area of the base, which is 4 times 5. 20 times 2 is usually 40. I could ask you, what about this one? What if I said, come on, let me write my R down there. Can you picture what that is? Right, I'm going from -1 to 1 and -2 to 2. What is my region then in the XY plane? There's my region. And then what is this shape? I mean, that's, again, a very terrible, terrible drawing. What is that? Cylinder, right? Well, actually not a full cylinder because I'm only above the XY plane. So isn't this half a cylinder? And how do you find the volume of a cylinder? Right? 1/2 pi, right? Half because it's half. It doesn't go all the way under. R, what's my radius? And what's my height? Right? -2 to 2, 4, and my radius is 1. Right? So if you recognize a shape and it is a known solid, your cylinders, your cones, your boxes, or whatever, don't have to do fancy calculus. But what if we do? I forgot to put that there. If I actually have to compute or evaluate a double integral, thank you, Fubini, I think. This Italian mathematician, as you can tell by his picture, right? He doesn't have a wig, right? Or fancy cravat or all that kind of stuff. So he is modern. I think he was doing most of his work during the kind of like the World War I era, if I'm remembering correctly. So let's take a look at what he says. He says this is a theorem. So he was able to prove if you have continuity on a region, then evaluating the double integral over that region where you are finding the areas of little rectangles, right? And then multiplying them by the height is the same thing as integrating. Notice the delta A has turned into delta Y, delta X, or delta X, delta Y. Notice now there are bounds on the integral signs, and they correlate to the X values and the Y values of your region. Notice order matters. The first integral has dy first, and so the inside integral has y values, and then the outside integral has the x ones, as opposed to here, where x is the inside delta, right? You have dx first, so the x values are on the inside. And we are going to think about working inside out. So let's do an example. So I have some surface. I don't know what that looks like, but let's pretend it's some surface up here. Right, here's my surface. And I'm down in my region is in the XY plane, going from 1 to 2. And 0 to 1, so I have some kind of rectangle here. Oh, that's so bad. So sorry. There's my region. And I want to find the volume of what this region is all mapped up onto that surface. But only x is between 1 and 2, and y is between 0 and 1. So I'm going to rewrite this integral. I'm going to turn dA into dy dx, or right? It doesn't matter. Fubini says it doesn't matter which one you choose. In this case, it doesn't matter. Sometimes your math is just a little easier, right? One way versus another. What's important, though, is that since I chose y first, I have to use the 0 and 1 on the inside integral, then x. And if I were to do this one, since I had x first, I'm going to do this one. If you want to do this one, make sure you get the same thing. That would be great. So here's how, and it's the same idea with partial integrals. I'm going to integrate here, which means treating x squared like it's a constant. Since I'm integrating with respect to y, x squared is just a constant. So what am I going to do? I'm really just integrating y. What is the integral of a constant times a function, right? Well, it is the function's integral times this constant. So I'm just going to get 6x cubed. I'm sorry, 6x squared is my constant. And then I'm going to integrate y. Y squared over 2. And I'm going to evaluate that. Now, I don't do this in Calc 1, but I generally try to do this in multivariable, where here, just to remind myself what I'm plugging in for. I'm plugging in for y. So y equals 0 and y equals 1. Right? That's what I'm integrating at. So, of course, this is 3x squared. Times 1 squared minus 3x squared times 0 squared. So, of course, I just get 3x squared when I'm done. Replace that whole gray box with x squared. And I'm going to go up here because I've run out of room. So I'm going to copy over the integral. I'm going to copy over just the dx, right? Because I'm replacing everything in my gray box with 3x squared. And I am going to integrate with respect to x, so I have to make sure these are x numbers. And now I'm down to a Calc 1 problem, right? So this is going to be x cubed over 3, which of course is just x cubed, evaluated at x equals 1 and x equals 2. So I get 8 minus 1, aka 7. Cubic units, right? That is the volume of that horribly drawn shape there. So again, I invite you to pause the video and to do the double integral the other way, and you best get 7. I'm going to do the exact problem in yet another way, right? So you can think of this as a second way, or you can think of it as a third. It doesn't really matter, right? Fubini gave us the way to take the delta area and change it into delta x, delta y, or delta y, delta x. Here is another theorem. And this theorem says if you have a product of two functions where one function only is in terms of x and the second one is only in terms of y, then the double integral over your rectangular region of the product of those two functions, given your rectangular region, your areas in your domain plane, can be broken up into a product of two integrals, an x integral times a y integral. Now, this only applies, of course, if you have that situation. But I do with this, right? So can you see that I've got a product? I don't have x's and y's mixed up together, right? They're mixed up, but since it's multiplication, I can, right, turn this into 6x squared, which I could call g of x, and y, which I could call h of y. And that is they are being multiplied together. Therefore, I can just multiply the two separate integrals, making sure that I keep the right numbers, right? The x values were 1 and 2, and the y values were 0 and 1. Of course, multiplication is commutative, so it doesn't matter which order I do these. So integrate 6x squared, and I get 6x cubed over 3, or 3x squared, evaluated and I get 3 times Whoops, sorry. This goes away, right? This is a 2 because it is 6x cubed over 3, so 2x cubed. So 2 cubed is 8. 8 times 2 is 16 minus 2 times 1 cubed, which is 2. So this part is 14. Integrate y, and I get y squared over 2. So I get 1/2 minus 0. And 14 times 1/2 is 7 cubic units. 6x squared y lies above the xy plane, so I did indeed find the volume of the space between the xy plane and the surface 6x squared y. So lastly for this one, let me just, and I've referred to it a little bit, but I just want to make sure that you do know that many of the properties that we had in Calc 1 we still have, right? So the double integral of some constant times a function is the same thing as, right, osmosis. Do you remember that? For those of you that had me for calculus, you can take the constant multiple and osmosis it out through. Oops, I forgot my R. Also, the sum or difference of a double integral is the sum or difference of the separate integrals. Oops, forgot my DAs. And then this one, which we, I don't know, I can't remember how often we use this one, but this is a nice one. Kind of not done a good job with my space. Let me erase. As long as you have continuity, you can break up the integral, right? So if you have a region, you can break that up. If you can break your region up, right? And of course, this is given that equals your whole region, right? This is going to be kind of useful for us. We also have average value, just like we did in Calc 1, right? Average value is the integral over the interval. Okay. Now, some decisions that you might want to make. When do I now? I have two, right? I have multiple ways of evaluating a double integral, right? To evaluate a double integral, do I have a known solid? If you have a known solid, you ban calculus. can you use Fubini? And when you use Fubini, and I really hope I'm saying his name right, but I feel terrible if I don't. If you use Fubini, is it easier to do dy dx, or should I do dx dy? And again, sometimes it doesn't matter. But look at, for example, this one. Okay, which, in this case, which one do you think is easier to do first, right? Do you want to integrate which one of those would you rather do first? So when you look at this one, integrating this with respect to y, right? I have a product of two y things that I can't unproduct, right? Do you remember that from Calc 1? Right? When you had a product, like this is why BC, right? Why you needed to take BC to get here. When you're trying to integrate a product that you can't unproduct and U substitution doesn't work, you need to do integration by parts. Ew. I mean, I can do it, but I really would prefer not to if I don't have to. So if I look up here, though, look at this one. If I'm integrating the exact same product, but with respect to x, remember y is now a constant. So for instance, let's say y is 5. This is integrating 5 sine 5x, right? That's a lot easier than doing integration by parts. So that's why you might want to look at Fubini. And then, of course, you also have, right, my product of only x times only y. Are you integrating only x, only a product of only x times only y? Then you can do separate integrals. Right? And a good example of that would be something like this. Right? Can you see how that would be nice, really nice to do? Because that one, again, now who's who? Which numbers go with which letter? I wrote dy, so these are your y values. And who's in terms of y? Times who? Right? And you're going to take those two answers and multiply them together. So the antiderivative of cosine y is negative sine. So sine of pi over 2 is 1, minus sine of 0, which is 0. And then the antiderivative, I'm sorry, this is positive, isn't it? The antiderivative of sine is positive, that one is negative cosine. And cosine of x is negative 1. Right, when you put pi in there and then negatize that, I get 1. And cosine of 0 is 1. Negate it. 2 times 1 would be 2. All right? So 3 different ways to kind of handle double integrals. I will see you next time when our region isn't just a rectangle.